Hi guys, welcome back to Data Every Day. Today we're looking at a data set of ECG data from various patients, and we're going to try to detect abnormal heartbeats in the data. So there's sort of two tasks in this data set that we could do. The first task is classifying one of 5 different classes of heartbeat, arrhythmia, in the data, and the other one is these guys, which is just classifying whether a heartbeat is normal or abnormal. So we're going to do the second one. If you look at the description, it says that each row, the final element of each row denotes the class to which the example belongs. So if we go over here, if we select the final column here, you can see this is actually, they're all zeros in the normal case, and in the abnormal case, if we go and also select that last one, you'll see that they're all ones. So this last column is the label column, where abnormal examples are labeled as 1 and normal examples are labeled as 0. Additionally, I believe it says that all samples are cropped, downsampled, and padded with zeros if necessary to the fixed dimension of 188. So see at the end here, we do have a bunch of zeros, and that's because if a signal is shorter, if the time series is shorter than 188 data points, then they'll get padded with zeros so they're all the same size. So a lot of the pre-processing here is already done for us. Let's hop into the notebook, and I'm only going to be using 4 imports today. So we're going to use the TensorFlow recurrent neural network, and so I have GPU acceleration enabled because it significantly improves the speed of training for recurrent neural networks. We're actually going to use a GRU, or gated recurrent unit, and that's included in TensorFlow. We're also going to use NumPy and Pandas just to work with the data a little bit, and then the train test split function from sklearn to get our train and test sets. So I'll go ahead and import those, and I want to load in the data. I have to load them in from 2 different CSV files today. So what I'll do is I'll create a list of data frames called DFs, and I'll use list comprehension to load in using pandas.readcsv each file, and I can grab the file path to, for example, the normal file path. The only difference between the file paths would be this part right here, normal and abnormal. So what I'll do is I'll delete that, and I'll replace that with x. And then I'll just iterate for x in normal and abnormal. So this way we have a list of the outputs from the pandas read CSV function, where each time it uses a different file path given by x being plugged into this, and x is normal or abnormal. So this should return a list of 2 different data frames. df sub 0 would be our normal data frame, where the final values are all 0, and df sub 1 should be our abnormal data frame, where the final values are all 1. So we can't exactly merge these 2 data frames yet. The reason being the names are not, they won't line up, they're all different. So what I'd like to do is rename the column names. So the way we can do that, we can just say for each data frame, for df in dfs, we're going to take df subcolumns, df dot columns, and set it equal to a list of numbers, so a range from 0 until the length of df dot columns. So what this will do is it will just rename each of these to an integer from 0 until the probably 187. So let's see that, run that, and then we'll take a look at df sub 0, dfs sub 0, sorry. And you can see now the column names do range from 0 to 187, and df sub 1 has the same format. So now that the column names are the same, we can concatenate them together using pandas.concat. So this will take two data frames, 2 or more. In this case, the list of data frames is just given by dfs, So we are concatenating along axis 0, which is the row axis. So that means on top rather than side by side. And if we look at what that looks like, you can see we have still 188 columns with the same column names, but now at the top we have the normal examples, and at the bottom we have the abnormal examples. So next I'd like to shuffle the data. Well, first of all, let's store this in data. Let's call that data. And I'd like to shuffle it. So we can do that by sampling the data. We can sample 100% of the data without replacement. So fraction equals 1.0. And I'll include a random state as well so that we always get the same results. And if we look at that, you can see, if we take a look at data now, well, let me try. Can't actually visualize it with that random state, so let me try it with 2. That's not working either. Oh wait, what happened? Oh, I wasn't looking at the end. Okay, let's keep it back to 1. Sorry. So at the end here we have, you can see the 1s and 0s have been shuffled around. So now we have a randomized data set. However, our indices are all messed up. So at the end here I'd also like to type .reset index. And if I leave it like that, then the old indices will be added as a new column. So I'm just going to include drop equals true here. That way we just shuffle the data and reset the indices. Alright, and it looks like this is about ready to go into the model already, because normally we would scale our data, but it looks like these values already take on the same range. In fact, we can pretty much assume that they all take on the same range because they were recorded using the same instrument. However, I might try scaling it and seeing how that affects the performance of the model. So now what I'd like to do is split off the labels from the rest of the data set. So I'll call the labels y, and I'll call the rest of the data that we're using to predict the labels x. So here's y. This will be data sub, actually not quotes, just 187 is the name of the column. And we'll just make a copy of it. And then x will be data.drop 187 from axis 1. You know what? It might be better, instead of calling it 187 over here, why don't we rename it? So we can say data equals data.rename, and we pass in a dictionary that's going to map the old column names to the new column names. So 187 will be mapped to label, and we're going to do that in axis 1. So if I run this now, the end we have label instead of 187. So now down here, instead of targeting the 187 column, I'll get label, and we're going to drop label to get our x, and we'll make a copy of that as well. Okay, so if I run this, we can see x looks like this, which is one less column. The last column has been taken off, and just y, sorry, is just the label column. So now I'd like to do the train test split. So a train test split function from sklearn, we can take an x and y and specify a train size. 70% is what I'll use. And a random state, because this function actually does shuffle the data again for us. 1 is fine. And this will take x and y and split it into a train set that has 70% of the data, and a test set that has the other 30%. So that will return x train, x test, y train, and y test. And we run that, take a look at x train. You can see we're now working with 70% of the original 14,550 columns, and we have the same number, rows, and we have the same number of columns. And y train would just be also 70% of the data, but the labels for each of these examples. All right, why don't I actually, I'll say over here, preprocessing. Okay, and this is pretty much all we have to do for preprocessing, just the split, because the scaling has already been done for us. All right, so let's start training. So the training today shouldn't be too hard, because, well, actually it's as hard as ever, but our preprocessing was very easy. So the input to our model is going to be a tf.keras.input, and we'll specify the shape. Shape will just be the second dimension of the X train, so actually it's 187, because each example is going to come in with a vector of length 187 columns. So we can get that with xtrain dot shape sub 1. So that will be our input. And now if we just use a regular neural network here, so like a standard 2 hidden layer neural network, tf.keras.layers.dense, let's say we use 64 activations and a ReLU activation function, and we pass in inputs here, and on the second layer we just do the same thing but we pass in x, and our outputs will be tf.keras.layers.dense. We're only outputting one value, which will be sigmoid activated, which means it will return a value between 0 and 1. And this value will represent the probability that we classify a given example as abnormal. So the higher this is, actually if it goes over 0.5, we'll automatically classify as abnormal heartbeat. And if it's under 0.5, we'll classify as normal heartbeat. So we're just going to pass in the output from x and then create our model, tf.keras.model. We're passing in the inputs as inputs and the outputs as outputs. Alright, then we'll compile our model. I guess we'll just run that. Model.compile. So we're going to use an atom optimizer. For loss, we'll use binary cross entropy, which is best suited for binary classification problems. And then metrics, we can use accuracy, and why don't we use AUC as well? AUC is better for dealing with understanding how the model's doing within each class. Alright, so now we'll also fit our model and we'll store it in history. We'll store the results in history. So model.fit, we'll pass in the inputs as xtrain and the labels as ytrain, and we'll give it a validation split of 20%. So we'll hold out 20% of the data to use to evaluate the model as we go. And then we'll give it batches of size 32. We'll train for 100 epochs, and we will include a callback function, tf.keras.callbacks .early stopping. And early stopping will just allow us to monitor a given value, in this case validation loss we'll use, and we'll include a patience value, which is how many epochs are we willing to wait before we stop the model. And so what it means is we're going to look at the validation loss at the end of each epoch, and if we notice that it's not improving anymore, we're going to wait 3 epochs, and if it's still not improving by the end of 3 epochs, then we're going to stop the training, and we're going to restore the weights from the best epoch. So restore best weights equals true. And this is just a nice way, because we don't want to minimize the training loss completely, because most of the time that just means overfitting our model. So by minimizing the validation loss, we're getting a sort of a glimpse of how it will perform on the test set, and therefore see the fit much better. So I'll run this, and let's see how we're doing. Alright, so we can see the validation loss is still decreasing, and the moment it starts increasing again, the model should stop. And it looks like it's might be starting to increase here. Yeah, it stopped. So it started increasing for 3 epochs, and then it stopped the model and restored the weights from the best epoch, which was this one, epoch 24. Alright, so let's see how our model did. Model.evaluate. On the test set now, we're seeing how the model is doing on the test set, and we're getting an accuracy of 95.5%. So this is extremely good, right? Really good. So let's actually save that value. I want to print out. We'll say results equals model.evaluate, and I will keep verbose on 0, and I'm going to print out model accuracy, or I'll say test accuracy. We'll display it to 2 decimal places, and we'll give it a percent because this is an accuracy value. And we'll format this with results sub 1. So if you look, results is returning 3 values, the first of which is the loss, the second of which is the accuracy, and the third is the AUC. So results sub 1 will just target the accuracy, and I want to multiply that by 100 to get a percent value. Then we will do the same thing for AUC, and I want to just push this up so that they're lined up. And I'll display this one to 4 decimals because I'm not using a percent here. This will be the result sub 2, which will just get the AUC value, and then we can remove the times 100. And I have to run this and check this. Okay. So you can see it's very good. Let me just copy this down because I now want to change the model and see if we get something better here. So currently, it seems like we're getting good results, but each example is being fed in, sorry, not each example, each feature is being fed in independently of the others. The model has no way of understanding the connection between features. It sort of considers them all as separate things. But if we use a different model architecture, let's say we, instead of using these 2 hidden layers, we're going to use a recurrent neural network, which means let's evaluate this as a time series. Let's take in each feature with sort of a memory of the past features. So every time it takes in a feature, it also takes in a state that summarizes the past views of the features. So you can think at each time step during the recurrent neural network training, it doesn't just take in a feature, but it takes in all the past features as well. And it loops it until it has seen all the features. So to do that, we can use a GRU. This is just a simplified version of a long short-term memory network. And we get that with tf.keras.layers.gru. And so a GRU also has some number of units like the dense layers do, and we'll just give it a high number. 256 sounds good. And then we can also enable something called return sequences, and we'll set that equal to true. And return sequences is basically saying instead of looping and then spitting out the final result, we're going to spit out a result for each loop. So those results will all be stacked on top of each other, and instead of it returning a single vector, it will return a matrix of all the vectors. And so because it returns a matrix, we're then going to have to flatten the output into a single vector again. So tf.keras.layers.flatten we'll pass in the output from GRU. And then the last thing we have to note is that the GRU layer actually requires that the input vector is 3-dimensional because it accounts for each input being 2-dimensional. So here we only have 1-dimensional input, for a given feature. Right? For a given feature, we're just taking in a single value, but the GRU also supports taking in multiple values for each time step, for each input. So we have to expand the dimensions to include another dimension. So if we look at xtrain.shape, currently it is a vector. Well, we ignore this part because this is just the number of examples. We're looking at the input here. It's currently just a vector of length 187. But if we call TensorFlow.expandDims on xtrain, and we want to specify axis 2, which would be the third axis here, and we get the shape of that, you can see it has added this extra dimension, which the GRU will accept. It will throw an error if we don't do this. So I'm going to include another layer up here called expand. That's just basically going to be this. It's tf.expandDims and we're passing in the output from inputs here, and we're expanding on axis 2, which is the third axis. Then we want to put the output from expand into the GRU, and then we're putting the output from GRU into flatten, and the output from flatten into outputs. And I think this should be good. So yeah, I'll leave the shape up there of the original input. Alright, and I guess we could have a summary of the model to see that. Okay, so here's the new model. We start with this vector of 187, of length 187. We add this extra dimension. That then gets fed into the GRU, which returns 187 different sequences, one from each time step. That's because we enabled return sequences. And each one is of length 256, which is the size of our GRU layer, the width of it. And then we're passing the GRU into flatten, which is just basically is multiplying these values together to get a single vector of length 47,872, and then we're using a dense layer to just bring that to our final output. So let's see how this performs. Let's compile and run the model, same way we did before. And this is where the GPU acceleration comes in handy. This will be very slow if we don't use it. And this might take a little longer, so I'll pause the video and resume it when it finishes. Alright, it has finished training, and as we can see, it has done extraordinarily well on the validation set. So let's see how it does on the test set. We'll get our results and print this, and you can see we actually have a substantially higher result. So 98.65% as opposed to our 95% from before, and our test AUC is nearly perfect, 0.9952. So you can see that using the recurrent neural network, we're actually able to generate better results. And that's because we are using a time series data set. So each one of these is sort of meant to be understood as a progression from the past, this is stepping through time as we go. So when you have this kind of data, a recurrent neural network is usually the best approach to take, and it usually beats just a standard neural network architecture. So that will sum up today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.